Okay, let's do a summary of the chapter again, so that maybe the ideas become more concrete now that we have gone through the whole chapter. Let's start with this dispersion diagram. Ignore this other convention. We looked at the wave number frequency diagram in terms of period and cycles per day or so. We had the equatorial Rossby waves, Kelvin waves, and the mixed Rossby gravity wave straddling this point here, which at low frequencies becomes dispersive, and then at very low frequencies begins to behave like Rossby waves. And then we have the eastward and westward inertial gravity waves. Looking at the summary, the Kelvin and inertial gravity modes are non-dispersive, and there is no differentiation between the phase and group velocities, so the energy is advected identically. Equatorial Rossby modes, on the other hand, they are dispersive, so all members of the ER family have westward phase velocities, but the long waves have group velocities that propagate westward, while short waves have group velocity that propagate to the east. We invoked this when we did the reflection from the eastern and western boundaries in the ocean, for example. The higher frequency mixed Rossby gravity wave has both phase and group speeds to the east, behaves like a gravity wave, whereas as the wavelength decreases, the mode becomes dispersive, and at low frequencies it becomes like a Rossby wave with group speed that is positive and to the east. So that's the difference. It's like a short Rossby wave because the wave numbers are high. Right? The form of all modes is dependent on the depth of the shallow fluid h bar. We saw that h bar modulates the equatorial trapping and so on. In general, eigensolutions for small values of h bar are more closely trapped to the equator than larger values of h bar. Both equatorial Rossby radius of deformation and the turning latitude go as h bar to the 1/4. So obviously choosing the appropriate h bar becomes very critical. In general, waves are more latitudinally extensive in a westerly basic state than in an easterly basic state. Rossby radius deformation has an expression with the denominator which has the background basic state velocity and the Doppler shifted frequency as well as zonal wave number. This is smaller for westerlies than easterlies. So for an equatorial Rossby radius where the zonal wave number is negative and the basic state is westerly and the Doppler shifted frequency is positive, this will decrease and R increases, Rossby radius of deformation increases. So we used potential verticity arguments to explain the impact on the equatorial trapping in different basic states for stationary basic state, easterly, westerly, and the meridional shear. Anything that modulates the equatorial trapping latitude or turning latitude is essentially working through, let's say, beta effect. It's reducing or increasing the effective rotation rate of the planet. So that's what widens or shrinks the latitudinal scale of the potential well that we keep talking about, that is created by the waves, right? The impact of latitudinal shear on modal structure and latitudinal extent is also significant. We had already seen that from the kinematics of equatorial waves that this could be important. In general, latitudinal shear tends to slightly increase the latitudinal extent of the modes. So it's not that big an impact compared to the depth change and the basic state going from easterly to westerly. Okay, group speeds of the low frequency equatorial Rossby waves and westward mixed Rossby gravity waves, so low frequency, are similar in magnitude to the background basic state. Okay, they are similar to the background basic state in terms of their speed. If this is the case, we have to worry about whether zero Doppler shifted group speed would create local maxima in wave energy density. So you get, let's say, some kind of a standing mode where the wave is adventing energy into that region and building it up. But at the same time, there are variations in the background basic flow. So the question we need to answer is whether or not the changes in the wave number occurring when a mode encounters a easterly flow makes accumulation of wave energy more likely or less so. Okay, I hope this is correct. Make sure that this is not easterly but westerly. Okay, the normal modes of equatorial upper ocean were also examined. The families of oceanic modes were identical to those found in the atmosphere, but we had two major differences. The phase speed and the group speed of the oceanic waves are much slower, an order of magnitude slower in the ocean than in the atmosphere. This allows us to assume that the atmosphere is always in equilibrium with the slowly evolving ocean, which actually led to one of the first successful ENSO prediction models, the so-called Kane-Zibiak model, where they coupled a steady state atmosphere to an ocean that was time varying. Okay, and it produced, still continues to be used for various ENSO process studies, but it was the first one to make a successful ENSO prediction as well. As distinct from the atmospheric waves, propagating ocean waves encounter coastal boundaries on both sides, unless you are in the Southern Ocean. At a western boundary, very high or low frequency eastwardly propagating Kelvin waves are reflected as inertial gravity waves or long Rossby waves respectively. So it depends on the frequency of the incoming Kelvin wave, which propagates eastward along the equator. Modes with frequencies between about a week and a month form coastally trapped waves that propagate poleward because there is no westward group velocity mode present in that period. Okay, that's the summary. I hope it's fairly clear what we learned in terms of waves and interactions with the mean flow and the strength of the equatorial trapping and how it depends on the depth of the fluid, the background state, and in special cases also the length scale of the flow field, the background state. Right? We will use these in the coming physics, but we have now the background of wave kinematics, prototype tropical systems, and equatorial waves in simple flows. So now we will add the complications, which makes the physics much more interesting. Nonetheless, tropics remain generally more linear than the mid-latitudes, where the baroclinic instabilities make for huge nonlinearities. In the tropics, you have convection to deal with, which is quite nonlinear, and we'll see how these things affect our dynamics of tropical atmosphere and oceans.